Ever wondered how convolutional layers work in deep learning? Today, we pull back the curtain on this pivotal component of deep learning. Convolutional layers, often the unsung heroes of image recognition tasks, play a vital role in making sense of visual data. At their core, convolutional layers are designed to automatically and adaptively learn spatial hierarchies of features from the input data. These layers are responsible for detecting local conjunctions of features from the previous layer. They help us see the bigger picture by piecing together the smaller local details. One of the prime reasons convolutional layers are so important is their proficiency in image processing. They excel at identifying patterns, shapes, and objects in images, making them indispensable for tasks like object detection, image recognition, and even medical imaging. Now that we've introduced convolutional layers, we're going to delve into how they work. So, fasten your seatbelts as we embark on this fascinating journey through the world of convolutional layers in deep learning. So, how do convolutional layers work in deep learning? Let's break it down. The magic happens through a process known as convolution operation, a mathematical operation that is the heart of how these layers function. Imagine a photograph, which is our input image. This photo is not just a picture to a computer, but a matrix of pixel values. These pixel values, ranging from 0 to 255, represent the intensity of colors in the image. Now, we introduce a new player to our game, small matrices known as filters or kernels. These filters are the key to detecting features within our image. They slide over the image, pixel by pixel, to create a new matrix. Think of it like looking through a small window pane at a larger scene, focusing on little chunks of the image at a time. But how does this sliding happen? This is where stride and padding come into play. The stride is the number of pixels we skip each time we move our filter. A stride of 1 means we move the filter 1 pixel at a time, while a stride of 2 skips every other pixel. Padding, on the other hand, helps us deal with the edges of our image. It's like adding a frame around our picture. With padding, we can apply the filter to the corners and edges of our image, ensuring that we don't miss out on any important features that might be lurking there. As the filter moves across the image, it performs an element-wise multiplication with the part of the image it's currently on. The results of these multiplications are then added together to form a single number, creating a new matrix known as a feature map or a convolutional layer. This feature map is a condensed version of our original image, highlighting the features that our filter was designed to detect. That sums up the convolution operation, but there's more to convolutional layers than just this operation. What happens after the convolution operation in a convolutional layer? Well, we introduce a bit of non-linearity to the mix. This is where activation functions come into play, like the popular rectified linear unit, or ReLU for short. These functions help to add complexity and depth to our learning model. They essentially decide whether a neuron should be activated or not, providing the non-linear transformations we need. Once we've added this non-linearity, we move on to the pooling layers. Now, these are crucial for a couple of reasons. First, they help to reduce the spatial size of the convnet. This means they're shrinking the input, making the network less computationally intensive. Second, they play a big role in controlling overfitting, which is a common problem in deep learning. Pooling layers ensure our model generalizes well, rather than memorizing the training data. After understanding non-linearity and pooling, we're close to getting the full picture of convolutional layers. So why are convolutional layers so crucial in deep learning? Let's recap. These layers are the backbone of feature detection. They use the convolution operation, a mathematical process that takes in the input image and a filter, or kernel, to produce a feature map. This operation is how our models can identify edges, shapes, and other complex patterns in the image data. But it's not just about recognizing features. Convolutional layers also introduce non-linearity into the model, using activation functions to ensure that the model can handle complex, real-world data. And don't forget the role of pooling layers. They help reduce dimensionality, making the model more computationally efficient without losing key features. These layers in combination make deep learning models more efficient, effective, and capable of tackling complex tasks. And that, in a nutshell, is how convolutional layers work in deep learning. Remember, mastering these concepts is a big step towards understanding and implementing deep learning models.